Hi everybody, I hope you're well. This is the last lesson of the semester, so I hope you printed out the pages. And today we're going to solve both exponential and logarithmic equations. So let's start with exponentials. It's an exponential equation because I have a variable n as an exponent. That's what makes it exponential. If we can rewrite our equation with an exponential on each side of the equal sign with the same base, then we get to ignore the base and just look at the exponents themselves. So let me show you what I mean. In this first example, on the left side of the equation, we have 2 to the x power, can't be rewritten as anything else. On the right side of the equation, however, 32 is a power of 2, so I can rewrite it as 2 to some power. Now, because it's a reciprocal, I need a negative exponent. So 2 to the 5th is 32, so 2 to the negative 5th is 1 over 32. Now that we've rewritten it with an exponential on both sides of the equation with the same base, I get to ignore the 2's that are the bases, and I just focus on the exponents. So this means that x has to have a value of -5 in order for the left side of my equation to be equal to the right side of my equation. Okay, so we'll do it again, and it'll be a little bit more complicated over here as we go. So on the left side, I have 6, which can't be rewritten as a base to some power. 6 to the first power is 6. So it's 6 to the 3x minus 4, nothing to be done on the left-hand side again. But on the right-hand side, 36 can be rewritten as 6 to the second power. So 6 to the second power, that's that 36, but then this is still being taken to the x plus 1 power. Now, if you remember the properties of exponents, when you take a power to another power, we're going to multiply. So again, we are going to rewrite the left side exactly as it was. And then this time it's 6 to the, and we're going to multiply 2 times this entire exponent, which is, it's going to distribute 2 times x and 2 times that positive 1. And again, once the left side is equal to the right side with the same base, we can ignore the base of 6, and we're just going to focus on the exponent part right there. So now we'll rewrite this entire equation as just 3x minus 4 is equal to 2x plus 2. Now it's a simple linear equation. We'll subtract 2x from both sides, add 4 to both sides, and x is 6. You can always take this 6, put it back into the original equation to make sure that the left side is still equal to the right side. In this example, we see that we have reciprocals, so that's going to tell us right away that we need negative exponents. So I'm going to rewrite this as 7 to the negative x power. Okay, that's the same as 1/7 to the positive x power. And then 49 is 7 to the second power, but because it's a reciprocal, I need it to be a -2. So again, on the left side and the right side, I have exponentials with a same base. We say common base of 7. So now I'm going to ignore the 7's. I'm going to rewrite this as -x equals -2. Divide both sides by -1, and x is 2. And if you take the 2, put it back into the original equation, you can see that the left side is going to be equal to the right side. There are occasions, it says note, you might need to isolate your exponential expression first. So when you look at this example, 4 to the x is the exponential piece. Times 6 is extra on this side. So I want to get rid of that times 6. So I'm going to divide both sides by 6. And what remains is 4 to the x power on the left is equal to 16 on the right. Now I can rewrite this 16 as 4 squared, And so we can see we can ignore the 4's and we can take this exponent is equal to this exponent. Okay. On the next example, the exponential part is the 3 to the x. We need to isolate it on one side of the equation, so I'm going to add 1 to both sides of this equation. And I get 3 to the x power is equal to 81. And I can rewrite 81 as a power of 3. It's 3 to the 4th power, so x equals 4. All right, so now I'm going to show you what happens when you can't rewrite the left side and the right side with the same common base. So we'll slide that right up. Okay, so this time we can't rewrite the two exponential expressions with the same base. So when that happens, we're going to apply what we call the property of equality for logarithms. That means if I do it to the left, I got to do it to the right. And so we are going to undo this exponential with logarithms. That's the job of a logarithm, is to undo or be the inverse of an exponential. So if I take the log base 3 of both sides of this equation, log base 3 of both sides, the left-hand side, the log base 3, undoes the exponential base 3, and all that remains is this x. And on the right side, I have log base 3 of 32. So there are a few different ways that we can find, this is the exact value. We can't rewrite it at a different exact value. But we can use change of base. If you don't know how to put this in your calculator and you only have common logs or natural logs on your calculator, then we would rewrite this as log of 32. That's a common log of 32. That means it has a base 10 divided by common log of 3. That's our change of base property that we did the last section. And then if you needed an approximate value, okay, make sure that when you're in your calculator that your this entire numerator is going to need parentheses, the entire denominator is going to need parentheses. Okay, so same thing over here. I can't rewrite 12 as 6 to some power. So I'll undo the base of 6 by taking a log base 6 of this, and then log base 6 of 12. If I do it to the left, I got to do it to the right. So this log base 6 of an exponential with base 6 will just give me x, and then I have log base 6 of 12. Again, if your calculator will put this in for you, that's great. If you only have a common log or natural log button on your calculator, then you'll need to use the change of base property. So this over here, I use the common log. That's a log base 10 where we don't write the 10, it's implied. Over here, let's go ahead and use the natural log. It doesn't matter, it'll work either way. So we take the natural log of the 12 and divide that by the natural log of this base 6, and that'll give you the same answer as if I use a common log. And then again, if you're going to put it in your calculator and approximate it with a decimal, you are going to need to make sure that you use parentheses around the entire numerator, then divided by, and then parentheses around the entire denominator. Just like in the examples up here, there are occasions when we're going to need to isolate our exponential expression. So in this situation, I would subtract this 0.8 from both sides of my equal sign. And then what remains is this 4.2 to the x plus 4 on the left side is equal to 4.9 on the right side. And so again, we're going to undo this exponential by taking the log base 4.2 of this entire expression. And if I do it to the left, I got to do it to the right. So this is going to be log base 4.2 of all of that. So here we're going to take x plus 4, because this log of this base undoes an exponential with the same base, is equal to log base 4.2 of 4.9. And then because we haven't isolated x yet on the left side, I'm still going to need to subtract 4 from both sides. So we are going to get an exact value of log base 4.2 of 4.9 minus 4. And you can put all that in your calculator using change of base if your calculator doesn't do this for you. So we have solved two different types of exponential equations. The first type is when we can rewrite the left side and the right side using the same base. And then if we can't rewrite both sides of the equation with the same base, we're going to need to undo the exponential using the log of that same base. So now we're going to look at solving some some logarithmic equations. They're logarithmic equations because you're taking the log of something that's unknown, an unknown value. So just like the first examples for exponential, notice that I have logarithms on both sides of my equal sign. That means a log equal to a log, and they have the same base. Because I have logs on both sides with the same base, we get to, again, ignore the logarithm and just focus on this argument has to be equal to that argument there. So this, what looks like a complicated equation, really just means that what I'm taking the log base 3 of on the left needs to be the same thing I'm taking the log base 3 of on the right. So now it's just a simple linear equation. So I'm going to subtract x from both sides, add 3 to both sides, and x is 7. You can put it back up here to see that you are taking log base 3 of 11 on both sides of your equation. Now, there are going to be times when we need to condense the logarithmic expressions, and that's using the properties of logarithms from the last section. Notice that on the left side of my equation, I have two natural logs that are being added. When you have natural logs, they have a common base of the natural base e. And so because I'm adding two logarithms with the same base, I need to multiply these two arguments here. This 2x plus 3 and then the 5. We're going to multiply them together and reduce this to a single logarithm. So I have the log, natural log of, and we're going to take the 2x plus 3 and multiply it with this 5 right here. That's all happening on the left side, and that should all be equal to the natural log of 35 on the right side. So I'm just going to simplify this for us real quick. So I get the natural log of, I'm going to distribute the 5 to both of these terms. The natural log of 10x plus 15 is equal to the natural log of 35. Now that I have it down to two logarithms, one on each side of my equal sign and same base, which is the natural base e, I can just focus on the arguments. This is 10x plus 15 is equal to, and then 35. Now it's a simple linear equation. Subtract 15 from both sides of my equation, and then divide both sides by 10. X is 2. Again, you can put it back up into the original equation, and you can either simplify or you can put it in your calculator and see that the left side will be equal to the right side. Okay, so sometimes you don't have a log on both sides. You have logarithms on one side of the equal sign and a regular number on the other side. That's this type. And so what we're going to do is first make sure that I have a single log on one side of the equation equal to a number. So I'll need to condense into single logarithms occasionally. And then we're just going to rewrite the entire equation. We're going to rewrite it as an exponential. So I'll show you what we mean. So first we're going to condense this into a single log on the left-hand side. So again, because my logarithms have the same natural base e, and because they're being added, the two logarithms, I'm going to multiply the two arguments. So this becomes the natural log of, and I'm going to multiply the 2x plus 2 with this 5. And then on the other side, I just have a number 2. So let's simplify what's inside here. This is the natural log of, and again, I'm going to distribute my 5 to the 2x and the 2. And then this is going to be able to be rewritten as an exponential. So I know that this natural log means that the base is e. So this is essentially, I'm gonna write it in a different color because you wouldn't normally do this, but we might as well have this quick conversation here. Natural log just means log base e of all of this. And so you're gonna rewrite it. You're gonna take the base e to the power of, the logarithm is always equal to the exponent, so to the power of this 2, and set it equal to 10x plus 10. And now we need this x all alone, so we'll subtract 10 from both sides of the equation. That leaves this. And then the whole thing on this left side needs to be divided by 10 to isolate this x right here. So we're going to divide both sides by 10. So my answer is going to be this x will be equal to all of this left-hand side, all divided by that 10 right there. So that is the exact value of that, value of x. Okay, so we'll do that again over here. Notice this time my properties of logs, this is the quotient property. This over here we call the product property when we multiply the two arguments. This is the quotient. So because the two logarithms are being subtracted, both with the same base of 4, but subtraction means we're going to take this argument and divide it by this argument of x. So we're going to rewrite it as the log base 4 of, and then the x plus 6 is in the numerator. It's going to be divided by this negative log here. We're going to divide by this argument of x. So this entire thing is the quotient when we condense the left side into a single logarithm. Now we're going to rewrite this as an exponential. So I'm going to take my base 4 out. I'm going to take it to the second power because a logarithm is equal to the exponent over here of 2, and set all of that equal to x plus 6 all over x. So a couple different ways to solve this. This is a rational equation. One way is to just, I'll do this in a little bit different color there. So put this 4 squared over 1, and then we could think about it as just like a cross multiplication here. So this is 16 times x along this diagonal is equal to x plus 6 times 1 is just x plus 6. We'll subtract the x from both sides of the equation. I have 15x is equal to 6, and then divide both sides by 15. X is 6/15. And 6 and 5 have a common factor of 3, so this is going to be 2/5. That's our exact answer for x. Okay. Occasionally, or sometimes, it'll be a little more complicated. We're going to look at this one over here. We have the log base 2 because I want to take both of these logarithms and condense them into a single log. They're both being added. They're both positive and being added. That means I'm going to multiply this x with that x plus 2. That's condensing these two logarithms into one. So we have x times this x plus 2 is equal to 3 on the right side. Now, I'm going to go ahead and simplify what we have in here. So this is the log base 2 of x squared plus 2x is equal to 3. And then we're going to rewrite this log is equal to a number can be rewritten as an exponential. So I'm going to take the base of 2 from here to the third power is equal to x squared plus 2x. Now it's a quadratic, and that means it's going to be a little more challenging to solve than just a linear equation. So anytime we have a quadratic, and this is going to be a trinomial because I have a quadratic term, a linear term, and a constant, we move everything to one side of our equation and then apply the zero product property. So 2 to the third has a value of 8, so I'm going to move that 8 over to the right side. Now I'm going to take this trinomial, we're going to move up here, I'm going to take this trinomial and ask myself if it can be factored. So because there are factors of -8 that add up to 2, this will factor into x plus 4 and x minus 2. And then the zero product property says I'm going to set each of these factors equal to 0 and solve. So x is either -4 or x is equal to 2. So now I have two solutions, and it says up here, always check whenever we're doing logarithmic equations. You always have to check to make sure that you're not trying to take the log of a non-positive number. So if you try to take the log of a non-positive number when you get these solutions, then we would call one of these solutions an extraneous solution. So let's go back up. We're going to take this -4 and put it back into the original equation. Notice that log base 2 of -4 can't be done. Logarithms, this x is in what we call the argument, is a power of 2, and 2 to any power would always give me a positive value. So this x can't be -4. So I'm going to take this and I'm going to call it the extraneous solution. And then I can take this to put it back. You're going to see that I'm going to get positive arguments. That's good. That's what I'm looking for. So that's it. That's solving both exponential and logarithmic equations. You guys will do the homework for this. There's a test on Chapter 4, and next Monday on the 11th, the final exam will be due for you guys on MyMathLab. Take care. I wish you all well. Let me know if you need anything.